Hello and welcome to today's lecture. Today we'll take a finer look at some of the topics related to beamforming and signal processing. So let's get started here. So we have taken a brief look at beamforming. Beamforming is a spatial filtering approach. So now you are familiar with filtering in general in the context of signals, right? So you may have heard of things like a high pass filter, low pass filter, notch filter, etc. Right? These are frequency filters, right? They take certain frequencies and reject them. They may be selective in terms of certain frequencies. Similarly, when we talk about spatial filtering, we essentially enhance signals from certain regions in space and we may suppress regions signals from certain regions in space. Now, beamforming is used a lot in a variety of applications, such as in RF, in audio signal processing, etc. For example, you may have a room where you have a speaker who's talking, and you may want the signal coming from the speaker to be amplified, but signals coming from sideways regions where other people are talking not to be amplified. So this beamforming is a very interesting and research active field, and here we'll be discussing it in the context of ultrasound imaging. So now this beamforming that we are discussing has two aspects. One is the transmit beamforming and the other is receive beamforming, right? And if you recall, we discussed DAS, or delay and sum beamforming. This is actually the simplest beamforming approach, which relies on a constant assumed speed of sound in soft tissue, and it was earlier employed using hardware circuitries. Essentially, you need delays, you need summers, and that's where hardware was being used. Nowadays, it's being implemented digitally. Okay. So if you look at the delay and sum signal, okay, so we are looking at a single line. It is going to be the sum of signals Si of t, where Si of t represents the appropriately delayed signal received by the ith element of the transducer. So essentially, if this is your transducer and you have several elements like this, I'm talking about the ith element, and I will vary from 1 to n, where n is the total number of elements, which may be something like 64 or 32 or 128 or 256, depending on what type of transducer you use. So this signal of the ith element will be appropriately delayed and summed, right? Now, in some cases when you're firing, right, you're firing using different techniques. For example, you may be doing synthetic aperture imaging, you may be doing plane wave imaging, you may be doing focus transmits, and we'll discuss that later. But often we also employ what is called as apodization. In apodization, we employ weights. So then your y delay and sum would be given by a summation so now these weights are applied. Okay. Now these weights are applied. So what's the meaning of these weights? Essentially, what's the strength of the signal that you are giving either on transmit or the received signal? That is what these weights signify. So now consider a transducer array, looks like this. And any point which is given by xk, zk. Okay. So we can assume a grid, and the grid's depth will be determined by the depth till which we are imaging, the width will be determined by the array aperture, etc. And based on that, in that grid we choose a particular location that may denote a particular pixel. So this coordinate is given by xk, zk, and the transducer coordinate is given by xi, and you can also say xi comma zi, but since this is a linear array transducer, it's a planar transducer, so zi is equal to 0. If non-planar, for example, if it is a matrix array, then zi will not be equal to 0. Okay, but in this case zi will be 0, so I am gonna replace this by 0. Okay, so any particular element in the transducer, like for example here or here, can be represented by xi if I consider this as the origin 0, 0. Okay, so let me write that down here. This is the origin 0, 0. Now what's interesting is we know the pitch of the transducer, right? So we know the element to element distance. So we essentially know the distance. If I choose the ith element, suppose this is the ith element, the coordinate will be known because it is the ith element from the origin, and we know the size of each individual element, we know the pitch, we know the curve, etc. So we can calculate the distance from the origin, right? And clearly this direction is the z direction and this direction is the x direction in a coordinate system. So if a signal is being received from this point, right, like this, at what time delay will it be received? So let's calculate the distance first. If I want to calculate the distance from any point on this array which is located at xi, right, then I can use the distance formula from coordinate geometry. So will be given by square root of xi minus xk square plus zk minus 0 square. If you remember, the z coordinates of these array elements are 0, that's why I am using 0, and so the time delay is essentially going to be dividing this by the speed of sound, so 1 by c xk minus xi square, or the either way around, doesn't matter, plus zk square. This will be the time delay, right? Now this is the delay in terms of how long the signal will take to arrive at the particular element, and as you see, based on this coordinate, now xk and zk are fixed because right now this is the pixel that we are evaluating. After we are done with this pixel, we will go to another pixel and so on and so forth. So basically k will vary across the grid. However, if you see, this xi location is going to also change, right? So accordingly you can calculate delays tau i's for the location xi. Now, the total delay, this is the received delay, right? So I'll call this is as received delay. Okay. Now the total delay is going to be sum of Tx is transmit delay plus receive delay. And it turns out that the receive delay can be calculated just like I mentioned earlier, but the transmit delay actually depends on type of transmission. Okay, so let's look at it. So first let's consider plane wave transmission. So here again we have some elements and xi is at any particular location of an element, and here you have a pixel xk comma zk. Now it turns out as this is a plane wave, so the entire wavefront will arrive at this point at the same time, right? So if you recall, in a plane wave, the wavefront represents a planar surface, so the entire wavefront will arrive at the same time, and actually if I want to calculate the delay, it is simply going to be this distance zk divided by c, because it is like a direct transmission, the wavefront is a plane. So I hope this point is clear. Now let's consider focus transmission. Okay. Now in focus transmission, you have what is called a sub aperture, right? You may be using some of the elements, let's say these elements, you will be applying a delay and an apodization, and you will be firing. So in this focus transmission, what happens is Ti of k can be calculated as 1 by c zk minus tau focal delay. So what do I mean by that? Essentially, to focus the beam like this, right, you have applied this delay here, and so each element will have a corresponding focal delay which is represented by this delay profile. Like for example here, the least delay may be applied to this element, the highest delay may be applied to this element. So I'll write it down. Essentially this represents my tau I focal delay. So what I am doing is I am subtracting the focal delay. So once I subtract the focal delay, it becomes like a plane wave. So I hope you agree with this. Once I subtract the focal delay, the wavefront will become planar. Now, if I have a tilted wave, right? So if I have a tilted wave, then what happens? By the way, I didn't discuss this for plane wave transmissions as well. So I'll go back here and I'll just revisit this point. For tilted transmission, for tilted transmission, your tau I of k will be 1 by c zk cos theta plus xk sin theta for a plane wave, right? And similarly, For focus transmissions, for tilted or angled transmission, right? Which means that this is like behaving like a phased array. Your tau i's will be equal to 1 by c zk cos theta plus xk sin theta minus tau I focal delays. So I hope this point is clear, how you can calculate the transmission delays. Okay. Next type of transmission is synthetic aperture imaging. So in synthetic aperture imaging, if you recall, xi zi, where I can choose zi equal to 0, so I'll just say xi comma 0. So if you remember, in synthetic aperture, each element is individually firing, right? So there are no, essentially there are no delays in transmission, or essentially no focal delays to worry about, right? So simply here, if I have a point at xk and zk, then I can calculate the delays simply based on distance, is 1 by c square root of xk minus xi square plus zk minus 0 square, right? So this is going to be my delay, and like I said, we need to sum up the transmit delays as well as receive delays to be able to get the total delays. So once I have the transmit delay and the receive delay, that is my total delay. So my process summary essentially is, first you estimate the delay and then you create S1 prime of t. Let's call this S1 prime of t my appropriately delayed signal. So this is, let's say my signal is S1, okay? So it is S1 t minus tau 1 t, right? Similarly, S2 prime t is my appropriately delayed signal. It will be the received signal t minus tau 2 of t, and so on and so forth up to Sn prime t, Sn t minus tau n t. So these are the total delays. These are actually total delays. And once you put these total delays, it will have the effect of bringing the signals in phase, and when you sum them up, then it will give the maximum possible signal. So first step, like I said, involves, this is what I call delay estimation. Okay, this is the first step. Then the second step will be apodization. So signal from each element is given a weight, right? So if you recall, let's say these are the elements in question, we will be providing a weight. This is my weighting function. So now remember, here when I am weighting in apodization, it is essentially a gain of the transducer elements in terms of amplitude. This is not the delay profile that I am showing you here. There might be a delay profile also that is associated, but this is the relative amplitudes which this function represents. What this tells me, that the center elements has the highest amplitude and the lowest amplitude is for these peripheral elements, right? So if I do this apodization, now if the weight WIT represents like W1T, S1 prime T plus W2T, S2 prime T, and so on and so forth. I'm gonna sum up all the way up to W and T Sn prime T. So this is my signal, which is also apodized with proper apodization weights. So if you recall, apodization literally means foot shaping. You'll recall that the word pod, like bipod or something, like it denotes foot. So foot shaping essentially means footprint shaping. Because the array aperture actually determines its footprint. So you are shaping its footprint by providing different weights to the transducer elements, right? So this is what apodization is. And if you recall, what apodization helps with aperture control. Okay, so it tells you how many elements are chosen and what are their weights. Okay, what are their weights? Essentially, what's the voltage signal profile that is given to all these individual elements. So typically changes with depth. This beam forming process is being done pixel by pixel, right? So as we are looking at pixels that come from shallow regions as well as deeper regions, we can choose to change the apodization, right? So apodization changes with depth. Why is that necessary? First of all, let's think about aperture. Okay, aperture. I think you must have heard of aperture in the context of camera imaging, where it denotes the the diameter of the sensor array that is used for photography, right? Similarly, aperture here, it represents the active elements, right, that are being used for this imaging process, and it is a combination of transmission as well as reception. When you are sending the signal, you may have a different set of elements. When you are receiving, you may have a different set of elements, for example, or a different number of elements. So the effective combination of that is our aperture. Okay. So let me define something called focal number or F number. This is also used in imaging, camera imaging, etc. So focal number is given by depth divided by aperture size essentially. Okay. Now consider like a single element disc transducer like this with a diameter d. For such a transducer, we can define, because this transducer has a fixed focal length, so F number is defined as focal length by aperture diameter, which is d, right? But here in our case, we can change the focus because we have an electronic array. So we are defining focal number as depth by aperture size. So what we do is we try to keep F number fixed throughout the image. As we go through the different pixels and we do beam forming for all those pixels, we try to keep F number fixed. So in that case, what this tells me, that if I have a pixel that's deeper, okay, it is located in a deep location, so then as you see the depth is increasing, that means the aperture size should also increase. Similarly, if I have a pixel that is located in a shallow region, then the depth is lower, so I can use a smaller aperture. So let me just write that down. Okay. Now it turns out there is something called dynamic aperture, in which you increase the aperture size as you go deeper to maintain same f number, focal number. Okay. Now it turns out sometimes it may be difficult because you may have limited number of elements in your aperture. So as you go deeper and deeper, it may not be possible to keep increasing the size of the aperture. But to the extent possible, what you would do is you would use more and more elements to fire and to receive as you go deeper in the tissue. So I'll just write that. So we grow the aperture, means use more elements, as we visualize deeper targets, and we do this to the extent possible because there may be limit to which you can grow the aperture. You may have limited number of transducers elements in your probe. So that is something we keep in mind. Okay. So with this, let's change gears a little bit, but let's talk a little bit about these advantages and disadvantages of apodization. So we looked at this qualitatively the other day as well, where we said that it reduces side lobes, right? So what are we talking about here? If you remember that if you have a source velocity and source velocity will take the same form or will be proportional to the aperture function. So here the aperture function is a rectangular signal, right? It's a rectangular pulse like signal. So if you remember, there is a Fourier transform relationship between the source velocity or the aperture function and the pressure field at focus. So if you take a cross section of the beam, right? So let's say this is the beam, and if you take a cross section, then what you get, you may get something like this, let's say, with the main lobe and side lobes. Now this profile that you see here is going to be related to the Fourier transform of the aperture function or the source velocity function. So in this case, this represents a rect signal, and so the profile looks like a sink signal, and sink, it has its own ripples or side lobes. So we would like to reduce side lobes. So rather, let's say, why should we do it? Why should we reduce side lobes? If you will recall, side lobes determine our contrast resolution. So we would like to reduce the side lobes. So what can we do to reduce the side lobes? If it's a single element transducer, there's not much we can do to change the source velocity function or the aperture function. But if we have an array of transducers, then I can apply an apodization like this. This will essentially smoothen the aperture function, and when I take a Fourier transform, then if I look at the profile, then I get a main lobe and my side lobes will become reduced now, right? So these are lower side lobes because of apodization. But as it turns out in signal processing, it's always a trade-off. To gain something, you have to lose something. So what do we lose here? It turns out the main lobe, okay, broadens. Okay, so what's the challenge with main lobe broadening? If you recall the lateral resolution, right? We talk about the lateral resolution as the ability to differentiate these two scatterers which are within the beam and outside the beam. If my main lobe broadens, then it adversely affects lateral resolution. Right? So it affects lateral resolution, but it improves contrast resolution. The other aspect is, if you are providing this kind of a weighting function, essentially you are telling this element and this element to fire, but with lesser energy because the weight given is less here. So reduced energy is transmitted, and reduced energy means lower SNR, and lower SNR in turn will mean lower penetration depth. So all these aspects have to be considered, but nonetheless apodization is used widely because of its ability to improve contrast resolution, and it sometimes dehazes the image if you go for apodization. Okay, so essentially after our beamforming process is complete, for each element we have summed the signal, right? If you remember the formula where we are getting y das t is equal to I equal to 1 to n si of t, where si is the appropriately si, or you can call it si prime of t, doesn't really matter. You can provide a weight wi. Now once you have this signal and you have summed it up, right, the next step would be a process of envelope detection. And then you would go for log compression, and you would show the image at the appropriate dynamic range. So 50 or 60 dB is very common for ultrasound images. Based on the application, it can be higher or lower also. For example, contrast enhanced imaging, typically when you're using nonlinear imaging, typically uses lower dynamic range because the majority of the dynamic range is occupied by the linear signal, which gets cancelled off. So the remaining signal occupies a lower dynamic range. Okay. Okay, the dynamic range, and then of course you have the image. You can do all kinds of post processing. You can do, depending on the type of image, some scan conversion may be needed, some filtering, denoising, etc., some image sharpening. All those post processing techniques can be done. There are a lot of proprietary algorithms as well for doing this that are implemented on scanners. So now this delay and sum beamforming is the simplest one. In our previous lecture, we just briefly touched upon some other advanced beamforming techniques such as minimum variance beamforming, robust Capon beamforming. We also discussed delay, multiply, and sum beamforming, right? Next, I would just like to discuss a very simple trick, which is a way to enhance the performance of delay and sum beamforming. So let me introduce. So this technique was reported in 1994. It is a weighting of the dash beamformer. So whatever signal you get from delay and sum, you take it and you weight it with this factor, and this factor is called the coherence factor. It is given like this. So if you look carefully, it's a ratio of coherent sum and incoherent sum across the array elements. If you recall, what's the coherent sum? In coherent sum, we take the phase into account. So here, for example, if we take these different signals, Si of t, or rather if you want to call it Si prime of t, that is also okay. But what these are the phase appropriately delayed signals, right? So if you take these signals, you sum them up, then the phase will matter, right? There will be constructive and destructive interference. So once you first sum them and then you take the energy is proportional to the modulus square, then you will get what is called the coherent sum. But if you first take the absolute value of the signal, then you will lose that phase information, and then you sum them up. This is called the incoherent sum. So if you take the ratio of this coherent sum and incoherent sum and use it as a weighting factor, it improves performance. Why does that happen? Let's discuss that. I'll write it first. Increased contrast and resolution can be obtained from coherence factor weighting of dash beamformer. And there are many other factors like that based on coherence properties. So for example, there is phase coherence factor, there is sign coherence factor, and you can certainly look into the literature, but nonetheless the basic principle remains the same. So the idea here is that if you have the signal coming from the main lobe, or you can say even focus, right? So let's look at it like this. Let's say this is my transducer array, and at this point I am in the main lobe of the beam, right? And the beam also has some side lobes, so I'm drawing those side lobes like this. There's another point which is located here, right? Now it turns out that the signals arriving from the main lobe, I am actually putting them in focus, right? Because I am applying delays by taking this pixel into account, and I am bringing all those signals in focus, in phase, and then I am summing them up. But when it comes to this term, not all those signals emanating from this location will be in phase, right? So the maximum coherent sum will be for signals emanating from the main lobe, and it will reduce for signals emanating from the side lobe, because of which we get some reduction in the side lobes. And as the side lobe drops, so do the artifacts associated with the side lobe. So I think this gives you a good information about beamforming, and gives you some details in terms of how it is actually accomplished. You can also look into how it is done computationally, how it is implemented on systems. But I think we'll stop here, and in the next class we will do a recap of beamforming and image reconstruction. Thank you.